Looks like we're live. Hello everyone and welcome to yet another recreational programming session with Mr. Azuzin. So let's do... not really. Yeah, starting soon. 5 minutes. Hello, welcome. So Yusu, so Pilot Red Sun, MPV, Shuffle, all of this jazz. I wanna brew a cup of tea. Super quick. Too loud. Too fucking loud. Hello. So, yeah. Yo! Stephen chat. Fucking Stephen. How's it going, everyone? Thank you for all of the subs. Erhan Kurnas 2000, thank you so much for tier 1 with message part 2 of 4 of setting up Vulkan stream. Well, I mean, hopefully it's gonna be less than that because we're not drawing a triangle, right? We're trying to do compute shaders. Quarter274, thank you so much for tier 3 sub. Jeffrey Bezos will be happy. I don't get anything from that, so don't waste your money. Unless you wanna make Jeffrey Bezos happy. So, if you like him, you're probably a huge fan of Jeffrey Bezos. CEO entrepreneur, born in 1964, Jeffrey Bezos. A lot of people like billionaires for whatever reason. I have no idea why though. Jeffrey Einstein. Yeah. Yeah, that's true. It's a famous scientist, Jeffrey Einstein. Jeffrey Bezos should stream programming on Twitch. Yeah, exactly. It's pretty fun. So is the compute shader for the rendered game? No, we're not using GPU for 3D rendered game. So I'm listening to you to sing to Jeffrey Bezos while working on Amazon building. Great. That's a level of irony we all want it. So I don't really know what's gonna be the plan for today, but I guess we're gonna continue just like, you know, pushing through the tutorial until we reach something. Though at some point we'll have to diverge from the tutorial because it goes to create a window and start putting some shit on the window and stuff like that, and this is none of the shit that we want. Right, so we want a compute shader, and I do remember that the tutorial had a section for compute shader, and maybe this is something that we'll basically jump into after we're done setting up the queues and logical devices and so on and so forth. We probably may want to look into the pipeline. So, MM, thank you so much for the sub with the message Spoopy13 over. Okay. Many people in the chat were saying that vulkantutorial.com is very outdated. I do not give a fucking shit. I'm fucking learning. For fuck's sake. Holy fuck. And you're not using the latest web frame. Fucking... Let me fucking learn, for fuck's sake. You freaking nerds, I swear to God. Oh, so annoying. That's why you're all single, that's why. Literally why. Does it seem more complicated than OpenGL? Nah, not really. Not really. It's kind of the same. To be fair, like there are pros and cons, like for OpenGL and Vulkan, right? So one thing I don't like about OpenGL compared to Vulkan, for example, is that it has a lot of hidden states. Right, I already talked about it in the previous session, right? So it has a lot of hidden state. And yeah, so you literally have to like know about it, about this implicit hidden state, and there's no way for you to discover that. Here, everything is explicit, at least so far. Right, at least so far, everything seems to be explicit. You create the structures, you explicitly pass the structure around. There's no like hidden global stacks or anything like that. So I kind of like that aspect of Vulkan compared to OpenGL so far. so did you know that I'm waiting for Govno stream for years already? A lot of people wait for a lot of different kinds of streams for decades already. So you're not that special in that regard, my friend. You are not that special. If you want to have a stream on a particular topic, do it yourself. So that's how internet works, right? So if you miss a particular kind of content on the internet, what do? You make it yourself. Okay. So what do we have? What do we have, chat? What do we have, chat? So I need to find where I stopped. So this is where we started to look for family queues and shit like that. And I think it was about creating like a logical device. So this is where we create a logical device. Then, yeah, where is the find? Yeah, find queue family indices. I think this is where roughly we stopped. All right, this is the next day and let's continue. So I think roughly we stopped somewhere here, right? So we stopped at creating VK device queue creating for, right? So we start roughly there and we actually need to find the queue family indices. So in this particular tutorial, they kind of did something really weird. Right, so if I take a look at the implementation of find queue families, where is it? People even mention it in the comments. You can now also use this for early exit from this one. Okay, so nothing particularly interesting. Where is the implementation of this function? Yeah, so essentially it returns the structure with a single index, right? It returns the structure with a single index, and they never really implemented this logic, right? So, and I think what they did later, right, so this is basically an implementation, but it's completely in a different place. Nice job, tutorial, like spreading code all over the place in different chunks and stuff like that. I have no idea how you expect people to even fucking read that, especially out of order, right? So, and in here, so I suppose they are searching for a particular family in here, right? So this is roughly what we do right now, right? So if I try to run this entire thing, let me see what's gonna happen. There we go. So we find a bunch of queues. Right, and I suppose we can basically try to do the same algorithm here. In this particular algorithm, it's kind of interesting. So it never breaks when it finds the particular bit. So that means it picks always the last queue for whatever reason. Maybe there is an explanation in here why it does stuff like that, but I'm not, don't want to read this particular text, right? So including types of operation now that we have this fancy family lookup function, don't care. So maybe there is some explanation why they always pick the latest one, but I'm too bored to fucking search for that. Like they should have put it somewhere here. I'm gonna assume that there's no explanation on why. All right, so what we can do in here, right? So we can maybe do something like a compute family, right? So this is a compute family. And essentially, if we found the compute family, we just do compute family equal to that current I in here. I wonder if we never found it, right? So what do we even do in here? So maybe we could do something like found compute family, right? So we could introduce something like this. Found compute family. So should have actually put U in here and it's going to be true. Right, so this is a compute family, and then we're gonna assert that we found the compute family. So now we can use this as sort of like the compute family that we want to have in here. So I think that's basically fair. Okay, let's go back to where we create VK device queue creation in for, right? So this is where we have to put this value and stuff like that. I'm really wonder like what is queue count? Like it's how many queues you want to create? Honestly, I don't know why I'm asking this question because I can just like look up the definition of this thing. So where is this structure, right? So we need to create this specific structure in here. So, and yeah, there is a bunch of flags. So there is a queue family index, we'll have to set it in here, and here is a queue count. So the reason why I'm kind of like really sussed out on the queue count is because there is a queue count in here, and I'm still not sure what the fuck it means. Right, so, and they don't really explain it anywhere, and well, unless we can maybe try to search for VKQ family properties, right? And maybe we can find some docs in here, some ref pages, but they're not gonna open because fuck me, I do not deserve to know anything. I do not deserve knowledge. I'm literally subhuman. Right, so I understand. So we'll have to find other ways to gather the knowledge. Right, so there's this kind of thing, maybe. Okay, so this is actually interesting. So is the unsigned integer count of queues in this queue family? Okay, this is interesting. Each queue family must support at least one queue. Okay, so it's just like how many queues of that queue family member or queue family you can actually create. Okay, I see. But then in terms of VK device queue, what is queue count in the context of this thing? That's what's interesting. So because in this context is how many you want to create, how many of such queues you want to create. So maybe we can actually, by the way, use this website. So this website doesn't consider me a subhuman, which is great. So that means maybe I can use that one. All right. So queue count is an unsigned integer specifying the number of queues to create in a queue family indicated by, okay. So how many of them you want to create? I'm not sure why you want to create several of them. And what does it even mean to have several queues of the same family? It's kind of like all very much abstract. But anyways, so let me maybe put this kind of thing in here, right? So let me put it in here, something like that. Maybe we're gonna actually zero initialize this entire thing. I wish I could just split my screen in two without losing all of the information in here. So, but anyways, I think it's too much to ask. So here we are doing tagged union situation. So we need to do VK structure type device queue create info, right? So create info. So that's kind of cool. So queue create info queue family index, and the family index is the compute family. So we created that, and then we are going to do queue create info queue count equal to 1, something like that. All right, so we did this kind of thing. And why it's so weird that they separated that into this thing. And the funniest thing is that why queue priority is a fucking pointer. Does that mean it will be modified? Yeah, look at that. PQ priority is a pointer to an it's an array of queue count normalized floating point values specifying priorities of work that will be submitted to for each queue. Okay, this is because it's an array. It's a fucking array. Okay. So that's kind of funny. Right, so and let's actually create this kind of thing. Since we have only one queue, we created only one queue of that specific family, we can just, allocate it on the stack and don't worry about it. So I suppose it doesn't really have to be allocated on the heap, right? So I hope the API is going to actually copy it like into some sort of internal storage or whatever. Hopefully. Okay. So, and it's kind of interesting. So what do we do next with this info, right? Maybe I want to go and just find where this particular thing is used. Is there any functions? So there's probably no function. Yeah, there is no function that accepts this kind of thing. So you have to nest it into another structure. Nice one. So, and this is exactly what we're doing in here. So now you have to, so VK physical device features, specifying used device feature. The next information to specify is the set of device features that will be used. These are the features that will be created support for the VK physical device features. Didn't we already call this function? I'm pretty sure we already called this function. So let me actually go ahead and just maybe search for this entire thing. No, but we never called it. We called the properties. So we called the properties of specific physical devices, but we never really called for features. So in the previous, these are the features that we queried support for in VK device features. I don't remember. I only queried properties. Right, I never really queried features, so that means I'll probably have to query the features now. And features and properties are not the same, okay. So in the previous, like geometry shaders, right now we don't need anything special. Oh, okay. So we can simply define it and leave everything to VK false. Okay, we'll come back to this structure once we're about to start doing more interesting things in Vulkan. Okay, so VK physical device features. Okay, so they just want like an empty struct in here. Right, so let's just create this empty struct for them. Right, so we defined what kind of queue we want. We defined like a physical device features, which is, I suppose, none. So now we're finally creating the logical device, right? So let's take a look at the definition of that logical device. Right, so here it is. And so here is the queue creation that we created previously, and here is the features, which is, I suppose, is going to be empty. So some of the fields in here are deprecated. So there is a PP enabled extensions. So PP extensions. So that's what we have. I suppose PP stands for pointer, right? So there's, as you can see, there's a double pointer. And what's funny is that they're using east const for the inner layer of indirection and west const for the outer layer of indirection, or vice versa. I don't know, like. So it's kind of interesting, right? But I suppose they do that to indicate that this is like a string, you know, array of strings. That's probably what they're trying to indicate in here, right? So this is a string, and this is a const array. So that means you can't really modify or reassign these pointers inside of this thing. So yesu. So let me maybe create this entire thing. So we're allocating this lstruct. We're allocating this lstruct on lstack. And zero initialize it, obviously. Zero initialize it. The next thing we say, we put a tag in here, right? So all of these things are tagged unions. And I suppose, I swear to God, this API was created by Rust developers. It was created by Rust developers because what they thought when they designed these different structures, they thought about an enum, right? So in their head, there was enum structure, right? And then inside of this thing, they had, okay, device create info, right? And then it had this kind of fields. Then physical device, this is literally what they had in their head. But since they're forced to program in C, they just basically translated the Rust to C. So, so yeah, anyways. Now we put the tag in here, right? So you put the tag in here, and then pq create infos, right? And as I suppose you can have several of them. Look at that. You can actually have several of them, right? So infos, yeah. So it's probably for each individual queue, maybe. Not quite sure. Queue creation, yeah, queue creation and info count. It's so like you can create all of this shit in batches, I suppose, which is kind of similar to OpenGL, I think. Right, it's kind of similar to OpenGL. You can also create a lot of things sort of in batches. Yeah. So several textures, for example, I think you can generate several textures like in batches, and I suppose this kind of inherits that. So anyways, examples are in C++ because they're ashamed of C. Honestly, C++ here feels out of place. I think they should have dropped it. The only advantage of C++ in using Vulkan is destructors, and that advantage only makes sense in production, right? So when you're writing like production level engine or something like that, well, yeah, you want to have like automatic destruction and stuff like that. But this is a tutorial, right? So, and they even said it themselves that they want to be as explicit as possible because it's a tutorial. Well, in that case, drop C++. So fucking be as explicit as possible. Anyways, so here we are given array of a single q create whatever, right? So single q create whatever, and so enabled features, no enabled features, I suppose, right? So there's no enabled feature. Okay, so that's pretty cool. There's a wall of text doing blah 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 blah, and do I want to read that? Do I want to read this kind of thing? Because it doesn't really feel that interested. So we populated all of that stuff. So, but maybe I can read it. So, the reminder of the information bears in a resemblance of the VK instance create and for struct requires you to specify extension. Yeah, I already noticed that. Yeah, so the pattern here is the following. Yeah, create and for instance, and so the commands, the arguments are basically packed into the structure. So I already noticed that. An example of device-specific extension is VK-KHR swap chain, which allows you to present rendered images. We don't care about swap chains. Again, we're doing compute. So previous implementations of Vulkan made a distinction between instance and device-specific validation layers. I don't care about the previous versions of Vulkan. I don't give a fuck. But anyway, so enabled extension count, right? So if enabled validation layers, we have to do the validation layers. We're not really enabling validation layers. Maybe I'm not gonna do that in here. So we won't need any device-specific extensions for now. Yeah, we already talked about it. Thank you so much. So now we're just finally creating the fucking device. Holy fuck, that's amazing. So let's take a look at the VK create device. VK create device. So here it is, and what we do, we provide the physical device. Right, and I suppose physical device is a handle, right? It is a handle, so it's going to be set to some sort of a value. So VK create info, and then the P allocator, and then VK device, right? So then VK device, and device has to be one of those things. Did we ever allocate a device? Oh yeah, we allocated the device in the field of the class that we're currently in, right? So I remember that device was the field or one of the members. I think that's what it's called in C++. Okay, so VK create device. I want to find the freaking function itself, right? So here is the function itself. And where is the physical device? Here is the physical device, and I just shove it in here. So physical device, and then create info. Yeah, so this is the create info, and it has to be pointer. Create info, boom. So P allocator has to be null, boom. And device, let's actually create VK device. I wonder if I already created VK. Yeah, I never created it in here. All right, so let's do the following thing. VK device, and this is going to be device. There you go. And I'm going to just put a pointer to device. Yeah. All right, so let's put it in here. And if I remember correctly, there was a result in here. Right, so, oh my God. Okay, so, and then we're checking that it's assert or not assert. So here we destroy an instance. I should have actually put all of that stuff in here. Okay, so if I try to run the whole thing, it doesn't compile because why? Use of undeclared identifier boolean, which is totally understandable. So let's actually go ahead and do std boolean. What else do you want from me? Create info, redefinition of create info. Fuck you. Okay, so we have create info. Maybe we should call this instance, instance create info, right? Something like that. Create info. So this one is going to be instance create info, and this one is instance create info. All right, so I don't think we don't need to. There we go, and everything worked successfully. But since we don't have validation layers, you know, enabled, we don't fucking know, right? So it's literally a gamble whether it is correct or not correct. So on top of this thing, I think I should also rename this stuff. So it's a device create info. There we go. So we have something like that. Isn't that poggers, chat? Isn't that poggers? I think it's pretty freaking poggers. Okay, so retrieving queue handles. The queues are automatically created along with the logical device, but we don't have a handle to interface with them yet. First, add a class, a member to store the handle. Who do you think I am? Some sort of a Java developer? We don't have a class. We're gonna allocate the shit on the stack. Fuck you. All right, allocating the shit on the stack. So graphics. No. We're not doing graphics in here. We're not doing graphics. We're not artists. We're doing computing. So compute queue. There we go. Compute queue. Device queues are implicitly cleaned up when the device is destroyed. Who do you think I am? We don't destroy anything. We let the operating system do its thing. Do its thing. So we don't need to do anything. We don't need to do anything at all, bro. We don't clean shit. So we can use the vk get device queue function to retrieve queue handles for each queue family. The parameters are logical device queue family, queue index, and a pointer to the variable to store the queue handle in. Because we're only creating a single queue from this family, we'll simply use index 0. Okay, I didn't understand shit, but maybe I should take a look at the signature of this function. So let's take a look at it. So there's a device, queue family index, queue index, and then this is how we retrieve the queue. Okay, so let's grab this entire shit. Let's grab this entire shit and just go ahead and try to put this stuff. So here is the device, au chocolat. So here is the device. Queue family index, that's basically that compute index thingy, right? So it's compute index, compute family index, right? So compute family. It's literally just called compute family. I didn't even call it compute family index. Am I an idiot? I think I am an idiot, but I might do an interesting thing. Let's call it compute family index. Not this one, this one, not this one, not this one, boom, and that's basically it. So in here, we can do compute family index. Compute family index. So it never fails. As you can see, it returns void. So fair enough, it never fails. It's so robust, it never fails. I'm still not quite sure what the fuck is queue index. I'm still not quite sure. And in here, this is the queue, and I suppose we just do compute queue, right? So this is compute queue. So I need to reread that one more time. The parameters are logical device, queue family, queue index, and a point. Since you can create several queues within a queue family, you need to specify the index of the queue you're referring to. Yes. Now I understand. Now I understand the point of this entire thing. Thank you. Thank you so much. So, and I suppose VKQ is a handle, right? Right, VKQ is a handle, and if we take a look at how the handles are defined, they are just pointers, and I want to just like double check that compute Q is some sort of a pointer, right, intelligible pointer or whatever. Might as well maybe start with null, right? So I'm going to initialize it with 0 and just run it one more time, and there we go. Here is the compute Q, right? So here is the compute Q. That's pretty cool. So we managed to acquire a compute Q. So, and we're done with setting up things. We're done with setting up things. So the next thing is presentazione. Windows surface, swap chains, image views, none of that is needed for us, honestly. I don't think we give a shit about any of that stuff because we don't even create a window. We just want to do a little bit of a compute. Though graphics pipeline basics is probably something that we don't want to skip. And yeah, so there's sort of like a pipeline. Yeah, maybe we do want to skip that. maybe we do want to skip that. Yeah, doesn't really help us at all. So maybe I'm gonna try to jump into the compute shader part, right? So there's a lot of stuff in here, and all of that is related to just graphics, right? So, and we don't do graphics, I just want to do compute. And there's like a huge section in here which is dedicated to compute. So, and yeah, so this is kind of cool actually. So the Vulkan pipeline, and there's even an example. That's great, actually great. Surely this won't backfire. I know. It's gonna be fun. So how we'll only streaming for half of an hour, so we have enough time for today. GPU. Nice, I like this term. So in this bonus chapter, we'll take a look at compute shaders. Up until now, all previous chapters dealt with the traditional graphics part of the Vulkan pipeline. But unlike all the APIs like OpenGL, compute shader support in Vulkan is mandatory. This means that you can use compute shaders on every Vulkan implementation available, no matter if it's a high-end desktop GPU or low-powered enabled device. It is mandatory. So this opens up the world of general purpose computing on graphic processor units, GPU, no matter where your application is running, GPU, no matter what your application is running. GPU means that you can do general computations on your GPU, something that has traditionally been done, been domain of CPUs. But with GPUs having become more and more powerful and more flexible, many workloads that would require the general purpose capabilities of a CPU can now be done on a GPU in real time. A few examples of where the compute capabilities of a GPU can be used are image manipulation, visibility testing, post-processing, advanced lighting calculations, animations, physics, for example, a particle system, and much more. And it's even possible to use compute for non-visual computation on your work that does not require any graphics output, for example, number crunching for AI. Oh my god! I just got a boner. This is called headless compute. And this is exactly what we need, by the way. They are talking exactly about what we need in here. AI mentioned. VC so advantages. Doing computationally expensive calculations on the GPU has several advantages. The most obvious one is offloading work from the CPU. Another one is not requiring moving data between the CPU and main memory and the GPU's memory. All of the data can stay on the GPU without having to wait for slow transfer from main memory. So aside from these GPUs are heavily parallelized, with some of them having tens of thousands of small compute units. This often makes them a better fit for highly parallel workloads than a CPU with few large compute units. Few large compute units. So the Vulkan pipeline, holy shit. It's important to know that compute is completely separate from the graphics part of the pipeline. This is visible in the following block diagram of the Vulkan pipeline from the official specification. Okay, so where is the... where? So draw, input... No, I see compute. Okay, so I like in here in the corner. It is obvious. Please consult the diagram, and it's a huge diagram. Please consult the diagram. In this diagram, we can see the traditional graphics part of the pipeline on the left and several shapes on the right that are not part of this graphics pipeline, including the compute shaders stage. I didn't process this phrase at all. We can see the traditional graphics part of the pipeline on the left and several stages on the right that are not part of the graphics pipeline. Yeah. Okay. So including the compute shader stage. With the compute shader stage being detached from the graphics pipeline, we'll be able to use it anywhere we see fit. This is kind of cool. This is very different from, for example, the fragment shader, which is always applied to the transformed output of the vertex shader. Okay, so I think I recognize these words. The center of the diagram also showing that, for example, descriptors sets are also used by compute. So everything we learned about descriptor layers, which we didn't, descriptor sets and descriptors are applied here. The foreshadowing. We haven't learned about the descriptors. Fuck. Why did they shove it somewhere between the graphics when it's also needed for compute? Fuck. Right, so we're definitely not gonna regret all of that. An easy to understand example that we'll implement in this chapter is a GPU-based particle system. Such systems are used in many games and often consist of thousands of particles that need to be updated at interactive frame rates. Rendering such a system requires two main components: vertices passed as vertex buffers and a way to update them based on some equations. The classical CPU-based particle system would store particles data in a system main memory and then use the CPU to update them. After the update, the vertices need to be transferred to the GPU memory again so it can be displayed and the updated particles in the next frame. Yeah, so this is exactly what I usually do on OpenGL, right? So because it's simulated in CPU, right? Then I upload all of that shit onto the GPU through its buffers and stuff like that, and then I try to put that on a screen, you know, through shaders and stuff like that. The most straightforward way would be recreating the vertex buffer with the new data for each frame. This is obviously very costly. Yeah. Depending on your implementation, there are other options like mapping GPU memory so it can be written by the CPU, called resizable bar on desktop system, and unified memory on integrated GPUs. Or just using a host local buffer, which would be slowest method due to PCIe bandwidth. But no matter what buffer update method you choose, you always require a round trip to the CPU to update the particles. With the GPU-based particle system, this round trip is no longer required, right? So vertices are only uploaded to the GPU at the start, and all updates are done in the GPU's memory using compute shaders. This is actually kind of cool, right? So for particles, usually your game logic does not depend on particles, so the game logic that is running on the CPU doesn't even care about exact positions of the particles anyway, right? So you know that the particles are updating somewhere on the GPU, right? But you don't give a shit about like what their current state is, right? And this is kind of interesting, right? This is kind of interesting. So vertices are uploaded to the GPU at the start, and all updates are done in GPU memory. Okay, so one of the main reasons why this is faster is the much higher bandwidth between the GPU and its local memory. So in a CPU-based scenario, you'd be limited by main memory and PCI Express bandwidth, which is often just a fraction of the GPU's memory bandwidth. When doing this on a GPU with a dedicated compute queue, you can update particles in parallel to the rendering part of the graphics pipeline. Oh, this is actually kind of cool. So you're rendering and simultaneously also updating the particles, but there should be some sort of like a synchronization mechanism, right? So this is called async compute, and it is an advanced topic not covered in this tutorial. All right, so when doing this on a GPU with a dedicated compute queue, and we already managed to acquire a compute chat, look, we've got the compute queue, holy fuck, it's a dedicated compute, we got it, it's talking about this thing. So with dedicated compute queue, you can update particles in parallel to the rendering part of the graphics pipeline. Oh, already, okay. Compute and advanced, why am I reading that? Did I just read it? I just read the same paragraph twice. I think I'm starting to have a dementia or something. So here's a screenshot from this chapter's code. The particles shown here are updated by compute shader directly on the GPU without any CPU interactions. It's static, motherfucker. Anyways, so data manipulation. In this tutorial, we already learned about different buffer types like vertex. No, we didn't! No, we didn't! I skipped that! I fucking skipped that! We didn't! Okay. Okay, maybe it's not that bad, because here, as you can see, they are they're still talking, like, they still explain how to create the buffers and stuff like that, so maybe it's not that bad. So in this tutorial, we already learned about different buffer types like vertex and index buffers for passing primitives and uniform buffers for passing data to shares. Well, luckily, I have enough OpenGL experience to kind of understand what the fuck they're talking about, right? So I'm familiar with things like vertex buffers and, you know, so index buffers, and also I'm familiar with uniforms, right? So that's kind of enough for me to understand what they're talking about, but I never seen this concept in a context of Vulkan, right? So that what worries me a little bit, but maybe it's gonna be fine. We'll see. And we also used images to do texture mapping. No, we didn't. But up until now, we always wrote data using the CPU and only did reads on the GPU. Yeah. An important concept introduced with the compute shaders is the ability to arbitrarily read from and write to buffers. Yeah, that's actually kind of cool point. Yeah, so because even from OpenGL, what I remember is that usually all of the buffers that you create, they kind of read-only, right? Right, and ability to write into the buffer is an interesting thing. And I'm pretty sure you can write into the buffers on OpenGL, right? Maybe there is some sort of extensions. And to be fair, you can kind of simulate writing into a buffer if you're, for example, rendering into the frame buffer. Right, so if you're just rendering to a frame buffer, you're basically writing into a buffer, right? And this is, I think, this is how we implemented literally smooth life at some point. Smooth life, right? Because remember this thing? Yeah, smooth life. So essentially, the state of the cellular automaton, a smooth cellular automaton, is stored within a single texture, right? And what we're doing, we're passing that texture through the fragment shader. Fragment shader computes the next state of the cellular automaton into the frame buffer, and then frame buffer is fed back into the texture, then is fed again into the fragment shader, right? So, and in a sense, fragment shader is writing into a buffer. It's just writing into it by rendering into the frame buffer. Does that make sense? So maybe, I don't know. But anyways. So shader storage buffer object. Shader storage buffer object. This is interesting. SSBO. Feedback loop. Yeah, it's a feedback loop. FP way of doing things. By the way, so another thing that FP people like to masturbate to is the fact that functional programming fits really well into parallel computations and you know, GPUs and stuff like that. Though at the same time, shader languages are not particularly functional. Have you noticed that? So there is this claim that pure functional programming is perfect for shaders, and yet all of the shader languages are still kind of imperative, kind of procedural, which is rather interesting. And I wonder why. So shader storage buffer objects. A shader storage object allows shaders to read from and write to a buffer. Using these is similar to using uniform buffer objects. I don't know how to use uniform buffer objects because I skipped it. The biggest difference are that you can alias other buffer types to SSBOs, and that they can be arbitrarily large. Okay, so going back to the GPU-based particle system, you might now wonder how to deal with the vertices being updated, written by the compute shader, and read, drawn by the vertex shader, as both usages would seemingly require different buffer types. But that's not the case. In Vulkan, you can specify multiple usages for buffers and images. So for the particle vertex buffer to be used as a vertex buffer in the graphics path, and as a storage buffer in a compute path, you simply create the buffer with those two usage flags. Okay, so VK buffer creating for, right? So we're creating the buffer. So VK usage vertex buffer bit, usage storage buffer bit, usage transfer DST bit. And I never really explained what the fuck is transfer DST bit. They probably did somewhere here, but we skipped it. Let's fucking go. It's gonna be fun, chat. It's gonna be fun. Right, so VK buffer create info. I'm pretty sure, like, I feel like I might have skipped some important information, but at the same time, VK create buffer requires device. We already got the device. Here is the device. Then it creates a buffer info. We're gonna fill in the buffer info, though they never actually specified what exactly we have to put in here. They never really specified. So here is null pointer and shared store. Ah, fuck. So we never got any of that stuff. Never got any of that stuff. So we get some subs. Right, so let me actually see. Thank you so much, DeForest, for Twitch Prime with the message. Thanks, King, for being an inspiration to do more AI. You're welcome. Dimon, thank you so much for the one with the message. Never heard Vulkan and fun at the same paragraph before. I know. So shared storage buffers, and there is an I in here, so that means they imply that we need to update something in here. I wonder if I can just put this thing somewhere in a separate place. Is there any search? I probably can't search within this entire thing because I kind of want to find what kind of thing they're referring to in here, and also create a function, how is it implemented and stuff like that. So maybe we should go a little bit back. Right, so how about we go to vertex buffers? Or maybe let's go into the drawing triangle. Right, so graphics pipeline, drawing, frame buffers, command buffers, rendering and presentation. So graphics pipeline, shaded module, fixed function, render passes, conclusion. Storage images, compute shader stage, loading compute shaders. This is almost what I need, but I feel like, yeah, I'm gonna spend a lot of time just fumbling with this thing. Because necessary information was buried deep somewhere between the shit that we don't give a fuck about, right? It's just buried somewhere within in here, and it's too much resources to just dig it out. And they don't want to give us just a complete isolated compute shader example because, of course, fuck you. So, all right, so maybe we can just try to Google something in here. Vulkan compute shader only example. Not gonna be using DuckDuckGo because it sucks ass for this kind of shit, so we're gonna be using Google. Fuck off Clunker, fuck off YouTube, don't give a shit, just, okay, finally. Vulkan minimal compute example. What do we have in here? Is it really minimal though? Right, okay, so there is a bot fractal, right, so this is actually kind of cool. The application launches a compute shader that renders a Mandelbrot set by rendering into a storage buffer. The storage buffer is then read from the GPU and set. So that's pretty cool. Thank you so much, whoever. Oh my god! This person understands what I'm talking. I'm not going crazy. So there are sane people on the internet who understand how the fuck is, you know, examples have to be designed. I'm not alone. I feel seen. Finally, I feel seen. Thank you so much. Holy fuck. Anyways, so I definitely gonna add that to le description, and yeah, so this is gonna be that. So we also haven't looked into VK guide suggested by by Kamikaze, right? So maybe we can take a look at that. But I actually want to start with this one. So let's actually read that. This is a simple demo that demonstrates how to use Vulkan for compute operations only. In other words, the demo does nothing related to graphics and only uses Vulkan to execute some computations on the GPU. For this demo, Vulkan is used to render the Mandelbrot set on the GPU. The demo is very simple and only 400 lines of code. The code is heavily commented, so it should be useful for people interested in learning Vulkan. So the only dependencies are Vulkan and Lodi.png. Lodi.png is simply used for PNG encoding. Vulkan can be installed from lunarg.com. Okay. So the application launches a compute shader that renders the motherboard set by rendering it into storage buffer. The storage buffer is then read from. Okay, well, ready. Okay, let's fucking go. Right. So there's shaders. Okay, that's pretty cool. This is compute SPV. That's very interesting. I suppose this is a. Is that a spear V? Sperm V. Sperm. So that means it's a binary, right? So it's a binary blob. It is a binary blob. Okay, so it's a sperm V. Right. So and it's compiled from here, right? And it's actually pretty straightforward. Look at that. I kind of like that. So sperm V example. So let's take a look at SRC. A single file. Single file. Oh my god. It's a single file. And it's so beautiful. It's simple. Holy shit. Classes. Motherfucking. Alright, so I guess we can deal with that. It's in the style. It's in the style of that freaking tutorial. Okay. Where is the dude? Where is my fell for it award? Literally fell for it. Oh, it's without the comments. Jesus Christ. Okay. So compute application. What kind of like? It's a Qt brainworm. What is this Qt brainworm that forces people to create this freaking class application? Like, you don't need a class application. Like, what? Just write the code like a normal human being. Come on. Or write the code like a clunker. You don't want to write code like a human being. Write it like a robot. Robots can just straight up put out like imperative code. They can also shed out a lot of this kind of bullshit too, though. But anyways. So the entry point in this specific case is run. You know what? I think I need to actually clone this repo, right? Because GitHub is ass in terms of like exploring the code and stuff like that. So let's go. We're gonna be third party, and let's just git clone this mother flipper. The mother flipper has been git cloned successfully. Let me go into src. So, by the way, what is this actually? I never heard about it. Is it better than stb image? I'm actually not sure. So, it might be more safe because I could imagine stb image maybe don't check ranges too much to save on space and everything. But anyway, so where is the render method? So it's probably run, not render, but run. Okay. So yeah, all of that is split like that. So buffer size, we're just allocate. Okay, so this is the buffer of the pixels. And the pixel is a structure which is, oh, okay, so it's basically vector 4, right? It is a vector 4. That's pretty cool. So to create an instance, creating an instance, I suspect, is actually pretty straightforward, right? So enabled extension, enabled validation layers, right? So we're not really enabling validation layers. By enabling validation layers, Vulkan will emit warnings if the API is used incorrectly. We shall enable the layer VK layer Lunarg standard validation, which is basically a collection of several useful validation layers. Why validation layers are like plugins? they implemented plugins for validation layers. It felt like they designed this API so you can sell additional validation layers. That's what it feels like, right? So they're optional. Well, I mean, I understand that. This is not what I'm saying. Okay, so here is the VK application. Okay, so this is the standard shed that we already done, right? Right, enable layer count or whatever. We created an instance, another validation layers. So this is just the creation of the instance. We already have an instance created. Okay, that's very cool. then find the physical device. Okay, I think we already done that. We already enumerated the physical devices, right? Oh my god, that's a lot of shit. So then we picked, as above stated, we do not feature checks, so just accept. Okay, so it literally, this is such a funny, why is that true? Kind of interesting. But I mean, it's probably explained in this wall of text that I didn't read. So we got a physical device. Okay, that's very cool. We got a physical device. I wish I could just quickly jump here. We created the device. Structure, queue family, device creation in 4. Yeah. So far, by the way, they're not really doing anything that we didn't do, right? So I feel like so far we did a correct minimal example up until the point where we need to create buffers. And this is where I kind of got stuck because I don't really know how to create the proper buffers and everything. So because you have to go through that, tutorial and everything. All right, so we have to do vk buffer create and for. Okay, so, and I think this is basically what they say in the tutorial is just they skipped a lot of important information that they could have actually put in here. Like you see, they skipped a lot of this shit. They could have put it in there, but they decided not to force you to go through this entire fucking tutorial. So structure buffer info, so this is the buffer size, and then vk buffer usage storage buffer bit. So in this specific case, we're only going to be storing data, not like we're going to be actually allowing vertex shader to access this data. We don't have this use case in here. So, and we also have a sharing mode, and it's a sharing mode exclusive. Buffer is exclusive to a single queue family at a time. Very interesting, very interesting. So then we create the buffer. We create the buffer. But the buffer doesn't allocate memory for its... Why? Why? I thought kind of... So in their world, the word buffer and the word memory are completely detached concepts from each other. Okay. So vk memory requirements. vk get buffer memory requirements. vk memory allocate info. Allocate info memory type index find memory type, which is a custom function. Then allocate the memory and then bind that memory to a buffer. Holy shit. Why? It feels intentionally anal. It just feels like, why is that? All right. Okay. So that's how we create le buffer. Le buffer. So one definition of pain, yes. So where is main.c? Main.c. So vk buffer create info. Let me go into the core, right? So vk buffer create info. So that's basically the thing we have in here. So that's the structure. That's the structure. And so structure type, you can also stack all of them and the usual stuff, obviously. So let's just put this thing in here and initialize it with 0. So vk type buffer create info, right? And so in here, buffer size. Buffer size is interesting, right? So because I suppose it is equal to, yeah. So it's the size of a single pixel. So in our case, a single pixel is just vector 4, right? And then multiplied by width and height. So maybe we can do something similar in here, right? So we're going to be just generating a single image. Though we could have, actually, I'm not quite sure what I want to do with the buffer. Right, let's also use image, why not? Right, so this is going to be struct, and let's say it's going to be vector 4, and in this specific case, maybe I can use la.h in here. Can I use la.h? I should be able to use la.h because I literally have, vector 4 in there. 2 days ago is a sus. I missed the context of this message. Okay. All right, where is the row? I want to take my library row. Okay, so here is it. Why it doesn't... Okay, it took a little bit of a time to actually highlight this specific row thingy. I pressed enter and I'm waiting, chat. Okay, finally. Though, to be fair, this is a pretty big file by itself because it is procedurally generated. We can take a look. Yeah, so it's 279 kilobytes, right? So, and it basically has 8,702 lines of code. This is Swizzling, by the way. This is it's a nice library, but it's a pure C library. It's a pure C library, but you can do Swizzling in here. Yeah, it's pretty fun. It's actually kind of funny because there are things like X, Y, Z, right? Right, and it's implemented as just taking a vector and returning itself, because like you don't have to swizzle anything, right? So it's X, Y, Z. It's kind of funny. But anyway, so yeah, for those who are interested, so you can find this library in here. And it's all procedural generated. I didn't write that manually, obviously. I didn't write that manually. So is like, what is going on with GitHub? It works like ass. It always worked like ass, but recently it became even more like apparent. Like it, holy shit. Did they stop writing codes? Right? Yeah. Finally, software engineering is no more. All of the software just falls apart. We don't do software engineering anymore. That's why everything is shit. Yes. So and in here we have v4f, and that's basically that. So and it's actually a union of several things. There's already built-in sort of swizzling of its own, right? But it's not as powerful as through functions. But then you can also access these things through array if you want to. So we can use that instead. But anyways, so 800 by 600. So this is what we're gonna be doing in here. All right, so the next thing, so main CPP. So we have to specify the size. So, and the size is, I suppose, VK device size. This is a separate type. Look at that. This is actually kind of interesting. So VK size. Oh, it's just type def and it's a uint64. Okay. I see what's going on here. So buffer creates info. Size is going to be equal size of v4f multiplied by width and multiplied by height. So that's basically what we have in here. So the kind of usage that we're going to promote is buffer create info usage vk buffer usage storage buffer bit. Yes. Usage storage buffer bit, and the next one, this one is a sharing mode. Not really sure what a sharing mode is, so but it has to be mode exclusive. One thing we can do is take a look at what kind of modes we have. So there is a concurrent one and maximum in. So there's only two possible VK sharing modes, I suppose. It's exclusive and concurrent. Okay. So, and the reason why we put exclusive in here is because buffer is exclusive to single queue family at a time. All right. So after that, we have to create the buffer. By the way, how do they define this macro? Do they do anything special in here? Oh, okay. So they say exactly where it fails. They utilize file and line. Oh, and they literally also use assert resource VK success. Right. And by the way, I think I forgot to, a very important thing, I forgot to give it a star, right? I think it deserves the star. Create le buffer. Create le buffer, sharing mode, vk create buffer. All right. Vk create buffer. Creating le buffer. All right. So this is the device. This is the device, and then buffer creation info. Buffer create info pointer p allocator. We don't need to allocate any p. Though we will need the VK buffer. Let's allocate the VK buffer somewhere here. So VK buffer, and I'm going to just provide the pointer to the buffer. And in here we have the results, right? So that's the result. Honestly, I don't see any point in doing this thing where they provide the location and stuff like that, because usually asserts, they also give you location where it failed. So kind of a little bit redundant in my opinion, right? So because assert will literally tell you where exactly it fired. So VK success. All right. So if I try to build this entire thing, obviously it didn't build because I didn't include la.h. Right, so let's do la.h. I'm not going to include implementations yet because we don't really need them, I think. And there you go. So it seems to be working, right? So it's so far everything is okay. Success. That's the motto of our channel. Suck that says. Okay, so now the fun part, allocating memory. We're already streaming for 1 hour, by the way, chat. Are we close to computing something on the GPU? To be fair, I can already estimate that myself, right? So because I can literally take a look. No, we haven't. Okay, so chat, go away. Right, so I'm only looking for the answer from people who I know, right? So different randos in the chat, they always debating me. Okay, so we only need to allocate the memory, then we have to create descriptor set layout. Okay, so what the oh my god. Set layout bindings. VK descriptor type storage, alright, so we have to create the layout. The descriptor set, right, so this is the descriptors that they talked about, right, so this is the descriptors that they talked about, that's pretty cool. Then compute pipeline, we're creating the compute pipeline. Okay, but I mean, it's not that difficult, right, so it's just like very boilerplating. Command buffer, right, we're finally creating a command buffer. Oh shit. And after we manage to create the command buffer, we're running command buffer. So how do we run the command buffer? So VK submit info, we shall finally submit the recorded command buffer to a queue. So this is the fences. I suppose the fences are for synchronization, right? So they're for synchronization of some sort. So there's fences and everything. Okay, so then... So yeah, so wait for fences, because it feels like some sort of a synchronization, like barriers or whatever. Ran command buffer, and then we save the rendered image, right? So we save the rendered image by, I suppose, oh, you have to map the memory. Okay, you have to map the memory. So, and I suppose it's already available after you just did VK map. And then we create an image, and then we unmap the memory, and then we just save this entire PNG. Pretty straightforward so far, right? So pretty straightforward so far. And I would say that we're 40% there. And obviously there's also cleanup, but I feel like we don't really need to do cleanup. I hope that operating system will do its thing, maybe. I really hope so. Yeah, that's pretty straightforward. I already spent 1 hour doing all of this shit. Already spent 1 hour. Debug report call back. So maybe the time has come to do a little bit of a break, chat. What do you guys think? So since you have iGPU, isn't your GPU memory just a regular memory? But does the Vulkan API give a shit? So, from the point of view of Vulkan, is it? So that's the real question in here. Vulkan doesn't give a shit, right? So whether it's a same memory, not same memory, you have to go through their API. If we programmed on a level of like drivers, maybe it would have made sense, maybe, but I'm not 100% sure. But since we're going through this sort of like a gatekeeper, of the GPU, like we kind of have to do all of these humiliation rituals, right? So because that's what they are, they're just humiliation rituals. Mem will have different properties. Bureaucracy, mental erosion. Yeah. No, it is literally humiliation ritual, right? So because a lot of like big corporations are invested into this API, right? So and they want to make the life of the developers as miserable as possible, so that only they can work with these kind of APIs, right? GPU hate. Well, yeah. So you're right. It's kind of similar to what you were talking about in the Discord regarding AI hazing. So it's kind of similar thing, right? So the only purpose of this thing is to demoralize you, right? So that's the only purpose of it. Because they don't feel demoralized by all of that. They feel nothing. They're a huge corporation. They can just pump out as many resources as needed to churn out all of that slop. They don't give a fuck. You are individual. You have to suffer because fuck you. So I always thought that the Vulkan triangle meme was just a meme. No, it's not a meme. It's actually real. So I think we need to make a small break, chat. I need to refill my tea, and yeah, we're gonna continue going through all that. Luckily, there's not that much stuff. It's just my approach is making it a little bit slower because as I'm going through all of these structures and all of these functions, I'm reading through their definitions and trying to kind of comprehend what they're doing. And maybe that's my problem, right? So because Vulkan, just like OpenGL, is not a real API, it's a copy-pastable API. You're not supposed to understand it, right? So you're not supposed to understand this API. What you're supposed to do, you're supposed to copy-paste it. Right, so and in the future, in the era of AI, you're supposed to just let the clanker do that. So anyways, let's make a small break, and after the break, we're gonna continue. So, boom. Resizing. Got stuck at resizing. CD, music, pilot, red sun, MPV, OGG, shuffle, muffle. Okay. Looks like there is a music. So, have fun. Hey yo, how's it going? So we're steeping le tea. So let's steep le tea. So we're almost there, chat. Hopefully we'll reach the end on today's session. Create a Vulkan. We're not creating triangle, people. Like, I can instantly see that you don't watch the stream, literally. I just can tell that you don't give a shit about what's going on the screen by just your message, because you have no idea what the fuck is going on. What kind of computation do you want to implement? I don't know. We can just do checker pattern, maybe? I just came, sorry. Well, just like I did into your mom. Yeah, it's okay. Don't worry about it. Pascal we can we can try to render triangle using compute shaders. Okay, fine. We can try to do that. So anything including matrices. Yeah. Software rendering compute shader. It's kind of interesting. If you do software rendering in a compute shader, is it software rendering or is it accelerated rendering? So too many new people. So are we getting botted again? Maybe. Thank you so much, Irish Rover Gaming. Tsoding is rather game of life and computer. Well, I mean, doing something interactive requires a loop, so I don't think we're gonna be doing that. I do not think we're gonna be doing that. Yep. It's kind of funny that, especially, it's interesting how anal it is to allocate the memory. I suppose maybe GPUs have different kinds of memories. Maybe that's what's going on. Alright, and you have to pick the right memory for a specific purpose and whatnot. That's cool. The GPUs feel like a completely separate computer. Right, so which you're interacting over a network, over the network or something like that. That's what it feels like. They are, yeah, they are basically a separate computer. So you're just like asking it to, you know, process some payload, and you get the result back. And you can kind of upload applications to that computer, right? So to kind of instruct how exactly you want to compute that payload. But yeah, not much. It's interesting, actually. It's interesting. Imagine interacting with all of the devices on your computer like that. Right. With all the devices. Each individual device is a separate computer, and you have to go through a very anal API like that just to get something done in there. Just wanted to say I've been a ton of your YouTube video series, love your interest and the way you explain problems. Your mindset really encouraged me to start learning C. I wished my mindset started to encourage you to learn programming, but I mean, people interpret it as an encouragement to learn specifically C. I have no idea why. Now I'm making a small GUI game. Appreciate you. You're welcome, I suppose. The reason why I program in C is that because it's the most non-language language to sort of demonstrate a point that language doesn't matter. And of course, every single person interprets it, oh, it's because it's in C. Okay. Guess it's pointless. Should have just programmed in Python instead then. Usually go to JS for probes. The problem with using JS is that it attracts a very weird audience of web devs. I don't mind programming in JS, but it's just like, people are so fucking tribalistic when it comes to programming languages, it's insane. Right, so I want the channel to be about programming, but I literally can't do that because there is a huge amount of tribalism in programming, and whatever language you pick, or you are that tribe now. You can't be just about programming. It's impossible. It's so fucking... I don't want to get banned on Twitch, so... Okay, so thank you so much, Sandix, for 30 months. Thank you. All right, so let me see. What did we get? Okay, we are back. Okay, so we created a buffer, but that's not enough, by the way. That's not enough. We have to allocate the memory. Where is the memory allocation? So we have to have memory requirements of fucking course. Memory requirements. Like when I do malloc, the only thing I can think about is the memory requirements. I can't just do malloc and give the size of the memory I want to allocate. I need to think about requirements, of course, obviously, fucking obviously. And yeah, so where is my core? What's the yeah? Oh, divide. Okay. That's the kind of requirements we're talking about. It's alignment memory. It's I see. Okay, CPP. And you have to get buffer memory requirements from the buffer. Fascinating. So yeah, okay. That's very interesting. Okay, so I'm getting these memory requirements. You probably want to actually maybe zero initialize it and shit like that. But at the same time, I also want to do maybe this kind of thing. So it's in 3. And I kind of want to go through that in le debugger. debugger. So cmd append cmd gf2. Right, so we don't really build with ggdb, but let's go ahead and do that. I'm going to do something like that, and I'm going to run this entire thing, and there we go. So here is the memory requirements. All right, so, and there's all of this stuff, and it's not even, why is it not 0? Ah, because I never really stepped through that, so it was not 0 initialized. All right, so then I get the requirements, and that's basically the size, memory type bits. So, and this is what we have as well. Is that really what I think it is? Right, so if I, for example, we have float, which is 4 bits. We have 4 of them, and then we have 800 by 600. Yeah, that's literally that. That's literally these sizes specifically. Okay, so nice to know. So we're extracting these memory requirements, right, and then we can finally do something with them. So memory allocating for. So it's additional information about allocating memory that is not just the requirements. Okay, that is very cool. Let's take a look at it. So it's yeah, of course, it's a tagged structure. This is the allocation size, right? So how much you want to allocate, and it's a device size, which is that thing. Yeah, that is kind of funny that it is, and you have to, yeah, this is the most interesting part. Find memory type, and it is a custom function. It is a custom function, and what's that custom? Oh my god. So I already actually have device properties. I think I already queried them, right? So, and I have to get physical, oh well, it's a memory properties specifically. It's a memory properties specifically. How does this search work? See the documentation for VK. Oh my god. Okay, so memory type bits. I'm iterating bits of a mask, right? If it is set, and there is something with these properties, we instantly. Okay, so essentially, we're trying to find like an appropriate memory type for this thing. So we know what kind of memory type bits we have, and then we have properties, and we're just trying to find the memory type, and it's literally an index in this thing. All right, so it's pretty cool. So we can structure, memory requirement size, specify the required memory. I'm not even sure, like, is it really necessary to do it like that? Because the only thing you specify from these memory requirements, look at that, is the size, which you can kind of compute yourself. Well, I mean, not the only one, it's a memory bits, right? So that's the memory type index that you have to specify. Wouldn't it be kind of cool if I could just assign memory type bits and Vulkan just does this bullshit for me? It's like, why is that up to me to do that? It's kind of weird. So then we're allocating a buffer, and then we're mapping and stuff like that. Okay, I think I get what needs to be done in here. I think I kind of get it. So this is just the requirements, right? So memory allocate info, 0 initialize that. That's the allocated stuff. And then we have to now find the memory type index, right? So this is where we have to set it. I'm going to put the to-do in here. And the things that we expect in here are this one. So these are the properties that we need. So host coherent bits, host visible bits. No idea what the fuck is that. Host coherent bits. So that means they could be incoherent, right? So that's what you're trying to tell me. So in the host visible bits. So it's a coherent and visible memory. So that means the memory can be incoherent and invisible. Do I understand correctly that there are use cases in graphics computing where your memory needs to be incoherent and invisible? Is that like what's going on? I'm literally confabulating it based on what I see in here. It's just like, is there a case for incoherent and invisible memory? Lazy allocated, incoherent like a stride. Is that what it means to be incoherent? I'm not really sure what exactly does it mean to be incoherent for memory. Cache can be incoherent. Ah, so that's what it means. Like in terms of like a cache, it needs to be synced across. Okay. So now coherent read and writes asynchronized visible memory updates are visible. But okay, so that makes sense actually. All right. So I just, in my brain, I didn't know that the word coherent in this specific case is related to cache. Thank you so much. All right. I'm glad that I actually started talking about it because I just learned what all that means. So, and there's also cached bits. So lazily allocated, protected bits, device coherent bit AMD, specifically for AMD. So specifically something for NV. So all of that is like, there's some vendor specific bits. Incoherent is more like not guaranteed to be synced between what CPU and GPU sees. Oh, and that makes sense. You know what? Going back to the particle system, as already said, particle, like the CPU doesn't need to know usually where the particles are located. So the memory that stores the positions of the particles does not necessarily has to be coherent. Okay, now it makes sense. So there is a use case for incoherent memory in case of a particle system, right? So if the logic of the game does not depend on the position of the particles, they're just specifically cosmetic effect that doesn't really do much in terms of the logic. Like CPU doesn't need to know where they're located. It literally doesn't give a shit. It's kind of cool. So yeah, so and because of that, so the API doesn't have to waste resources on synchronizing all of this shit. It can be incoherent and it's totally fine. That's actually, yeah, that's actually a cool example of that. That's actually cool. All right. So let's freaking go, mine from the freaking go. I actually want to inline this specific logic, right? I want to inline this function. I want to actually kind of compute it directly. So physical device memory properties. All right, so here is the memory properties. Might as well maybe put it in here. Physical device memory properties. Cool. Get physical device memory properties. All right, that's pretty cool. And as far as I know, in terms of physical device, where's my core? This is just a yeah, it's specifically physical device and not even logical device, mind you. Specifically physical device. Physical device, right. So this is a physical device that we have in here. Then we get the memory properties and we get this entire thing. And VK, can it fail? I don't quite see that. It cannot fail. Great. So this is a memory properties, and we can also take a look at this. So memory type count, and yeah, okay. So there's a heap. Oh wow, okay, so there's a memory type and there are specific heaps in there and they're kind of separate. So VK memory heap is what? Device size, memory heap flags. Jesus, that's a lot of... You can customize a lot of aspects of this entire stuff, right? It's kind of crazy how much you can customize. So we get that, then we're going through all of the memory types, right? And here is the memory type bits, and so this is the specific bit, and we're checking that. Yeah, so that bit, if that bit is set, we are taking the property flags of that specific type, checking them against requested properties in here, and if it is equal to itself, so that means it matches exactly, right? And I'm not even sure. Yeah, so that means it checks whether all of the bits are set in here. All of the bits that you specified in here, all of them are set, right? If all of them are set, that's the one that we want to put in here. That's kind of the logic in here, I think. So I want to actually rewrite that logic. I don't really like how it is written. So the way we're going to actually approach that is, all right, so memory type count, right? So I'm going to grab this entire thing. If this thing is not set, I continue, right? So I only care if that specific bit was set. So then in here, in a property, I take the property flags, right? Memory types, memory stuff, property flags. And the properties that I care about are these ones, right? That's the only properties that I care about. The way we can maybe check that if not, right, so we are checking against this bit, we're checking against coherency bit, and if it's not set, we continue, right? So, and then we're checking against visibility bit, and if it's not set, we go away, right? And if we went through all of these guards and found what we wanted, there you go. We can now set memory type index to I and break out of this loop. I think this is a better way of doing that, because it's just a little bit more explicit. One thing we can do, maybe just factor out this entire thing into property flags. Property flags, this one. I'm not sure if it's 32 bits, but here I'm gonna just assume that it's 32 bits. And then I'm gonna look it up. So memory properties. So where is my core? It's 32. Oh, well, I mean, it's a memory type, and then property flags. And the property flags is enumeration. So in here, I can probably put something like this. Yeah, there we go. So this flag is in set, continue. This flag is in set, continue. All of them are set. So we found the index, we get the fuck out of here. And that's how we're gonna be doing all of these things. So though, memory property, where do we get memory properties, right? So we getting them in here, right? And so you can think about this block of code as initialization of this specific field of this specific structure. So this block is sort of like a sub-initialization of this structure, right? And I really want you to explicitly do that, inline it so you can read actually top to bottom, right? So because one of the things about this this specific example is that you have to jump between different functions. In my opinion, it's not particularly convenient. It's not particularly convenient. So yeah, so ASM, we don't really need ASM in here. So memory requirement, memory allocation, we got this entire thing, and we initialized everything. So let me try to, so memory beats. So where did I fuck up? So memory beats. It's a memory beats that were taken from that thing, from memory requirement memory bits. Yeah, that's where they are. Memory required memory bits. So this is where we got them. All right, so and in node.c, in terms of gf, I'm gonna put 0 in here, right? So I'm gonna literally disable all of that stuff. It's pretty cool. It's pretty cool. It's pretty cool. So in terms of CPP, right? So now what we have to do, we just have to finally allocate a memory. Okay, so how do you allocate a memory? So you have to provide logical device. We were acquiring all of the types and stuff like that from physical device, and then we're gonna pass that information to logical device, which is kind of weird. So what if we like acquired some information that is not explicitly supported by the logical device we created? Can we have such situation? We probably may have such situation, which probably will be caught by validation layer, which we didn't enable, by the way. But anyways, so it's gonna be fun, chat. Trust me, it's gonna be fun. So Yesu. So device, what is that? Just a regular device. Memory allocation info. So it's allocate info. Allocate info. Allocate info, and this is going to be a memory callback null and device memory. So this is, I suppose this is basically what we need to allocate in here. Memory. And what is the device memory? It's just a handle, nothing particularly interesting. So yet another handle, and obviously this thing. So it's going to be a res, and then assert res equal vk success. All right, and everything seems to be okay, right? So as you can see, nothing broke so far. Nothing broke so far, and okay, where were we doing all this stuff? And after that, we have to bind the memory to the buffer. Okay, so let's take a look at this specific function. Right. So this is the device, this is the buffer, this is device memory, device size, which is actually memory offset. So you can, oh my god, so VK buffer is a slice on VK device memory. Do I understand that correctly? Because you can actually bind that buffer with an offset to the memory. That's what it is. They're basically slices. Yeah, the VK buffer view. Yeah. I see. See how it is. So that's why they're separated concepts, right? So because you can I rebind buffer at runtime, right? So for example, if I do draw call, it performs at a particular subset of memory. Then I rebind it to a different place, another draw call, and it will do it with a different subset of things. I think, yeah. So that's how it's used, I suppose. It is recommended to allocate bigger chunks of memory to assign parts of them particular resources, as there are limits to maximum number of memory blocks that can be allocated. So you're supposed to sort of like create atlases and shit. Anyways, so let's go ahead and just like bind the point. So VK buffer, it's just called buffer. So then memory and offset is going to be 0. All right, so this is going to be resource equal to that. Assert res equal vk success, and let's try to run that, and it is sucking says. All right, we allocated buffers, right? So we allocated buffers and shit. So descriptor set layout. Even though I kind of inlined everything, maybe it would make sense for me to just, you know, turn it into blocks, like separate that into like specific blocks so I can clearly see. Create buffer. So I obviously probably need some sort of buffers, some sort of blocks in here as well. But I'm gonna actually start delimiting buffers like blocks starting from here, right? So not to waste too much time on all of these layouts and stuff. All right, create descriptor set layout. A descriptor set layout. Descriptor set layout binding. So binding 0, descriptor type, storage buffer. So I suppose what the descriptor set layout does, it describes the layout of the buffer, because buffer that we allocated, it's just raw bytes. And then we need to describe Vulkan how interpret that raw bytes. So we have to provide the layout. So then it can map it in a shader to specific maybe attributes and whatever. So it's kind of like OpenGL. It's basically OpenGL, but 90 degrees. Like semantically, it's very close to OpenGL. I think, because so far all of these things kind of feel familiar. Right, so it's just like, yeah, it's basically OpenGL, just like it's like syntactically different. Bindless, I have no idea what is bindless. It's like it's like a playthrough, bindless playthrough of the API of the Raylib speedrun. Well, it's a successor to OpenGL. OpenGL is implemented on top of Vulkan, really? Is it implemented on top of OpenGL? I'm not sure. Okay, so let's see. I want to take a look at. So far, this one is actually relatively straightforward, to be fair. It is actually relatively straightforward. So this is a binding, though I'm not really sure what the fuck is this binding, though I think we can actually go ahead and just copy paste this thing in here, specifically vk descriptor set layout. So I can use this website. So structure specifying descriptor set layout. What is binding? Is the binding number of this name entry and corresponds to a resource of the same binding number in the shader stages. Oh, I think I know what the fuck it's talking about. It's probably corresponds to the number of this thing. Oh my god, it's literally called layout. So essentially what you're describing in here, right, what you're describing in here, it's binds to this. No, it's not. Oh, fuck, okay. So it's this one then. Oh, even binding is, okay, I see. So what's this one though? What is this one? STD 140. Oh, you can even specify the type of this thing. So it's a buffer buff. So then there's extension and okay. So what's the output of that? So image data. Oh, I suppose you just use that as an input and output. Let me see how it is used. Yeah, so you don't really use it as an input, but you just write into it. You just simply write into it. So there's also global variables and stuff like that, global invocation ID. Yeah. And by the way, sperm v, right? So it's a bytecode. Oh my god. Oh my chat. A new banger topic. If I manage to run to manage this thing work, I can maybe create a language that compiles into sperm v bytecode, which could be a banger stream, honestly. It could be literally a banger stream. So just like a custom, yeah, B to sperm. Maybe we could make a custom like a B backend. Yeah. So we can make a language that just spits out sperm v. That's a pretty cool idea. I really like that. B continuation, yeah. Sperm C. All right, so that's kind of cool. I wonder what's this format, right? It doesn't even have any magic, or maybe this is magic, right? It's kind of difficult to decipher what this thing does, except maybe string literals, right? So I can clearly see string literals, and I suspect that's kind of like maybe uniforms or some other things. Like, I'm not really sure why this thing needs to know the names of these things. Maybe for error reporting or whatever. But anyways, okay. So this is the set descriptor, and then you have to create an info. All right. So where is the main.c? And what are we doing in here? Descriptor set layout. Descriptor set layout. Descriptor set layout. So in here, I'm just creating this stuff. Just creating this stuff with a 0, right? With a 0, and so that's the thing. I just want to have this stuff around because I think it's going to be beneficial. Okay, so the set layout, and then so we set in the binding to 0. All right. The descriptor type, vk descriptor type storage buffer. What's that? Okay, so this is like different kinds of buffer, right? So in our case, if we're working with compute, it has to be storage buffer. I do remember that. So the descriptor count, I suppose, is how many descriptors you're going to have. Descriptor count. Is the number of descriptors contained? Yeah, so you can have several descriptors in here, right? So you can batch them, I suppose. Stage flag, shader stage compute bit. Okay. Okay, so then descriptor set layout create info and its additional parameters in there. So, and in here, what's that? So this is like basically tagged thing. So descriptor set layout create flags, and this is the binding. So it's kind of like, I see. Oh God. All right, so this is the stuff. Kind of. Just a second. 6. Then we go to CPP. I'm creating that stuff. 0 initializing. So the type is just that, nothing particularly special. And then the bindings count is just we have only 1 in here. And then we are assigning that descriptor set layout bindings that we created above. Right, so that's what it does. And then we just have to create the whole thing. Interestingly, are you serious? Okay. Oh, okay, so that's kind of interesting. Descriptor set layout. I have to provide that and then create info. Set layout binding. So descriptor set layout is probably like a global variable. Not really global, but it's one of these things, right? So we need to have it somewhere here, right? So we'll probably have to put it in here, which also means that we'll have to extract some of these things outside of the block so they're visible between the blocks, but we can do that a little bit later. So in CPP, we need to create a set layout. So where is that function? That's what we do in here, right? So we have the device, create info. So the create info is literally this thing. It's going to be at, so create info, p allocator, it's null, descriptor set layout, and it's just like what we have to put in here. So descriptor set layout. So we need to put that to the pointer, and obviously this entire thing can fail. So assert res vk success, and it has to be double equals, of course. So let's see if it didn't fail at least. Okay, so far so good. Okay, we described the layout. Even though, yeah, we didn't really provide that much information about the layout. We just kind of, we just described the type. So the only point was, yeah, so the only useful information out of this much code, 13 lines of code, is this and this, I suppose. literally just to pass 2 flags in here, 2 bits of information, this is how much code we need to write. Just to, and okay, so sure. Sometimes it does feel intentional, but I don't know. Okay, so this is a create set layout. So create descriptor set. So this is another thing. Descriptor set. So we'll allocate a descriptor set here. Didn't we? Wait. So it's like with buffer and memory. So you have descriptor set layout and then separately descriptor set, and we have to bind them together. Or is oh my god. So the classical descriptor model is as Kronos even acknowledges this. Yeah, I'm glad that they acknowledge that. All right. So descriptor VK structure. So descriptor pool size. Let's see what the fuck is that. Descriptor pool size. Structure specifying descriptor pool size. Thank you. So that is the type of the descriptor. Descriptor count is. 2 hours have passed, by the way. 2 hours have passed already. How close are we? How close are we? Let's actually see. So we only need to do this descriptor set shit, right? Only this descriptor set shit. So then we need to create. We haven't even gotten to compute pipeline. All right, so we'll need to create a compute pipeline. I think we can like kind of halfway through. We're kind of halfway through. So and yeah, so then we have to create command buffer, creating a command buffer. And then we run in the buffer, and we haven't gotten into compiling the shaders and stuff like that. 70%. It doesn't feel like 70%. It actually feels 50%. Just think about how amazing it will feel to see something on the screen. Another one. All right. So let me take a small break in a sense that I maybe want to put some flags and stuff like that. Right. So blocks. I mean, I keep confusing them. Blocks and flags, property count, right? So this is a property count. We enumerate all of that shit. So I suppose this has to be at the top, right? So because that, like, everybody uses that. So we can enumerate instances, property count. We can get different properties. Do we even use any of these properties anywhere? So it's not particularly used anywhere. So then these properties, we're allocating them, right? So we're allocating them, but then I don't feel like we use them much. So if I go and just reassert all of that stuff. Oh, they are, well, yeah, they're used within this thing, then within this thing. Okay, so I feel like this entire block is kind of useless, because what this block does, it just, you know, queries the properties and then just prints them and whatnot. Properties underscore properties. Right, so we got that. And we're leaking the memory all over the place because it doesn't really matter, to be fair. None of that matter. So checking the Vulkan properties, because that's what it is. Enumerate instance extension properties, and this is the core, and doesn't even require any instance, right? So you can just query the properties of the instance without querying the instance itself, right? Which is rather convenient. So here we're creating an instance. Yeah, so this is probably going to be something like that. So create an instance. Let's put it like this. Create instance. I just want to go through this code and just like see right, what kind of like sections we can have in here. So physical device count, I suppose here what we're doing, we're creating a physical device, right? So we're creating a physical device. And I feel like that's about it. Though we already kind of have block, look at that. We already kind of have block. And then we just do that. So get physical device property, get physical device queue family properties. And at some point, where do we actually create the physical device? I do not quite remember. So do we set it somewhere? Ah, yeah, I think I remember. So we pass a pointer. Yeah. My monitor has that. Okay, here it is. I think I found it. I think I found it. So this is where we create. So essentially we enumerate all of the physical devices, but since we expect only one physical device, we essentially treat this variable on the stack as a array of a single element, and this is where we get the physical device itself. Right, and this is basically the creation of the physical device. Get physical device. And we only have one physical device, which is like an AMD GPU in our case. Right. So we might as well get some properties. Well, we do need them in the future, I think. We do need them. So, and in here, what we are doing, get physical device Q family, we are, I suppose, creating the queue, right? We're creating the queue at some point. Found compute family, devices, then this is the logical device. It's kind of difficult to separate this block, so maybe I'm gonna omit that. All right, so my break is over. So this was just basically my break. Just go through the codes and maybe, you know, separate some of the things just to get an idea. So 200 lines of code, by the way. 200 lines of code. So Valiga, what's up? Probably used to have GPU driver crashes counter when he did a lot of Vulkan stuff. You might need one too soon. Well, I mean, we haven't even started yet. So we haven't even started. To crash the GPU, you need to actually upload something to the GPU. So, but we haven't managed to even upload anything there yet. We managed to allocate some memory, as far as I can tell, right? So that's already kind of good. Now let me think. So this is CPP. Create set layout. It's descriptor. So this is what we just did, and then descriptor set. This one I called descriptor set layout. This one is descriptor set. So this is a descriptor set. And yeah, descriptor pool size. You need a separate structure for that, of course. You really need a separate fucking structure for that. So it's interesting how there's a lot of substructures, but quite often, for whatever fucking reason, the substructures are pointers, which raises the question, why? Is that... Well, I mean, I see one reason why substructures are pointers is so when you change one of the structures, only the size of this structure is changed, and it doesn't affect all of the other structures it's inside of, but like some of the structures are like literally only included once within other structure and never again, which raises the question, what's the point of this structure exactly? Right, what's the point of exactly of the structure? Can anybody tell me? Like, what's the point of it? Like, why don't you just fucking, like, what is that? Right, you can always dismiss all of my rants as, oh, you're not a graphics programmer, you don't know what you're doing, the complexity is justified, all of that is justified, we do need that. Motherfucker, explain to me why is this needed? What kind of graphical programming use case does this kind of shit serve? Array? Oh yeah, array, okay. I'm sorry. So yeah, I don't know what I'm talking about. So confirmed. It's an array. Yeah, it's just an array. See. All right. So let me try to do. Let's continue. So this is a descriptor pool size, and let's put this stuff in here. So this is gonna be 0. Descriptor type, storage buffer, and descriptor count. Okay, so there's only one in here. And the next one, I hate that at some point I get so frustrated with this API that I kind of stop trying to understand it. And it's like, when you stop trying to understand it and you just start copy-pasting it, you realize that all of these corporate motherfuckers won. Like, it's just like this kind of, this feeling inside of you is just like, they fucking won. They fucking won. They humiliated you to the point that you don't care. And this is exactly how they get you. This is exactly how you get you to the point that just like, yeah, I don't care anymore. I'm just gonna copy paste. I'm just gonna copy paste. I'm not gonna try to understand. And they're not gonna try to understand. And this is how they turn you into this fucking zombie, the copy-pasting zombie. And once you turned into this copy-pasting zombie, they can only say, oh, now you are automatable, because now we have a robot that can also copy-paste shit like that. So this is basically how it's happening, literally. Right, so they're like mentally abuse you to the point that you're a robot, and now we can replace you with a robot. So fucking crime against humanity. Crime against humanity. All right, what do we get? CPP. Create descriptor pool. I'm not sure what the fuck is a descriptor pool. So if in a case of descriptor set layout, I kind of understood what it is, right? So, but what the fuck is a pool? We'll allocate the descriptor set here. So create. I have no idea. What's the point of pool then? I thought we're kind of done with descriptor layouts. Like what? So device, descriptor pool creation and for, and so on and so forth. All right, so we're creating this kind of thing, and I suppose it can fail, right? So it is can fail. So assert res equal to vk is success. That's what it is. With the pool allocated, we can now allocate the descriptor set. Right, so the descriptor set was not even properly allocated. So that's what you're trying to tell me. So it was not even properly allocated. I fucking hate that I just like feel so demotivated that now I have to copy paste. Like I fucking hate that. Fuck you whoever designed this API. Genuinely, fuck you. You know what you're doing. I despise you personally. So VK success. All right. Don't even freaking tell me that all of that shit is justified. I don't believe you. You did that intentionally. Like, I'm actually 100% convinced that all of these people are doing this shit intentionally. All right, so there's a descriptor pool, but we never really allocated that descriptor pool anywhere. Descriptor pool. So it's probably one of these things in here, yeah. So we're gonna be doing that stuff, something like that, right? So this is gonna be, and a descriptor set. But though descriptor, didn't I allocate descriptor set? I remember quite vividly that I think I did allocate descriptor set. I wish I could find it. Nah, I only allocated descriptor set layout. So that's what's interesting. So only allocated descriptor set layout. So here's the descriptor pool. Then we need descriptor set layout. Descriptor set. Yeah. So let's put it in here. And that should basically do it. All right, at least nothing broke so far. At least nothing broke. So where was I? Let's go back. So we already allocated them. Descriptor set layout. So descriptor buffer and for, right? So okay, descriptor buffer and for. Right. Descriptor buffer and for VK descriptor set. Okay, and then we update descriptor sets. Though, how do we bind descriptor set layout and descriptor set together? Where do we do that? Descriptor set. I need to find it. So here's the descriptor set and layout. Yeah, they are basically connected in some places in here. Yeah, so they're kind of connected somewhere. So VK update descriptors. So I suppose this one never really fails. This one never really fails. Yeah, it doesn't really return anything in particular. So let's put that stuff in here. Okay, buffer. Okay, this one is interesting. So it wants the buffer, but I don't remember it complaining about the buffer. Yeah, so here it is. Here is the buffer. And the buffer size. Did we ever specify buffer size? We never really specified buffer size. And this is because we did this thing. We can, okay, so we can maybe factor it out into buffer size, sure. And I don't quite remember what was the buffer size. Was it uint32? I suspect it's a uint32. So it's a buffer size of some sort. So CPP, buffer size, and it's uint, yeah. Okay. Yeah, and I hate it. I absolutely hate that they demoralize me to the point that I just don't feel like it's worth even looking into that. Like, that's how they kill the joy of programming. That's why everybody hates programming today, is because of people like you. People who design this shit. You personally, you killed programming. You killed the joy of programming intentionally. I hope you get paid well for that. You fucking traitor. Descriptor set. So compute, create compute pipeline. Compute pipeline. So what do we have in here? And yeah, so now we have to do this kind of shit. So this is just only creating the compute pipeline. So, and this is where reading sperm v, right? So this is where we're reading sperm v, and we're just like allocating, associating, and stuff like that. That's kind of interesting. So this one, maybe it's worth trying to understand it. We already have, by the way, read file, by the way. So we already read file. So knob.h. Do I have knob.h? Where is this thing? So knob.h, read entire file. So we can just employ this thing to read the file. We can just employ this thing. And where is the CPP? Create compute pipeline. So create compute pipeline. All right. So, and it's actually uint uint32, which is weird. So VK shader module creator info. So if you take a look at the core.h, code is you. Oh, wait. That is interesting. You telling me that LSL, it is it divisible by 4? It is divisible by 4. Look at that. It is divisible by 4, which means the entirety of the bytes of sperm v bytecode is just an array of uint32s. This is interesting, actually. This is interesting. Where is the chat? There we go. Now, let's go back. I hope I didn't modify too much in here. Yeah. So there's some. Oh, Emacs actually just stripped of the white spaces. Stripped of white spaces. We need to, since we're starting to compile shaders and stuff, I think what I need to start doing is to figure out how to compile the shader. At the beginning of the session, right, at the very beginning of the session, what we did is we tried to compile this thing, right? And I remember that we didn't manage to do that. So we used GLSLC, right? So, and I just tried to do something like this, compute shader. So compute shader requires a particular extension being enabled. And I do remember at the beginning of the session that it didn't explain to me how exactly to enable this specific thing. But here we have an example that actually shows how to enable particular extension. So maybe we can just do that. This one, separate shared object. I'm not really sure what the fuck is that extension, but okay. So let's try to maybe enable that in particular extension, right? So this is that, and yeah, so enable. Okay, so it seems like it picked up. So linking compute stage, missing entry point. Each stage requires one entry point. Doesn't explain what kind of entry point like it wants, but I suspect it's something like main. Okay, so it's something like C essentially. All right, so let's do void main, and yeah, we can just keep it like that. Is it gonna be enough to compile? There we go. A sperm V. Look at that. Google. Oh, it's because excuse me. It's GLSLC is actually compiled. Is actually developed by Google. That's why. All right. So can I have something like O and just have main SPV? Was it SPV? I think it was SPV. Yeah. Oh, it is SPV because it's a.spv. All right. So what we can do, by the way, we can add that as a part of the compilation of the main project, right? So we can grab all of these things and just put stuff like that, right? Just put stuff like that, and this one is weird. CMD append CMD like so, and then we're gonna execute that. But I suppose we can actually compile them in parallel, right? So we're compiling them in parallel. So this is gonna be procs 0, and in here this is gonna be async procs, and let's do it like that. All right. Seems to be compiling. About that. Okay. So maybe we should actually collect all of that stuff into a separate build folder or whatnot. So to not clutter everything, we can try to do that, right? So I want you to make sort of like a mental break from all of this Vulkan mindfuckery. So I'm gonna just like spend some time on the build system, right? So build folder is going to be build something like that. So sort of like a brief moments of like break, right? So I can just like enjoy something else. All right, so make dir if not exists, build folder. If it doesn't work, we're gonna just put it like that. So here is the main, and it's a build folder main. Okay, that's pretty cool. And this one, the output has to be build folder as well. All right, so what we want to remove is all of that stuff. Okay, so what didn't work out, because it was also trying to run the whole thing. Right, so it means it has to be build folder. Look at that. Look at that. Does not exist. Fascinating. Why it doesn't exist even though I said created there? Right, so I said create this thing, then I tried to run it and it couldn't run it because it doesn't exist, even though it does in fact exist. Where did it go? I forgot to actually do a fence, right? So there should be some sort of fence. It's going to be procs flush, right? So this is going to be procs. If not working, return 1. Return 1. All right, so that seems to be working. It would be nice to have some sort of like a round flag. Some sort of a round flag. Give me bool run false. And just put all of that stuff behind the round flag, which we can parse a little bit later, maybe. And this one, look at that, there's sort of like a debug here. We might as well introduce like a debug flag, why not? Right, so this is debug flag, let's flush, and let's just put that behind the debug flag. Kind of cool. So, and now in here, we can have a very simple program name, parser, shift, argv, argc. And in here, we can just do something like argc, c greater than 0. So this is going to be called char flag. So shift, Something like that. If strcmt flag, what is that? Run equal to 0. Run true, otherwise one of these things. Run debug. It's going to be debug. Otherwise, we can maybe say that something like unknown flag. Maybe even use the log system. Yeah, unknown flag. That. Right, so I'm gonna put flag in here and return 1. Something like that. Right, so a bunch of flags in here. So it would be maybe better to use flag.h, but it was kind of faster for me to do this kind of thing. All right, so this compiles. I can now run the whole thing, and if I want, I can even debug the whole thing. So I can break main, right, and run the whole stuff, and maybe not. And then at some point, okay, just run it, or maybe just build it without running it. It's pretty cool. That's pretty cool. So, notice how programming just flows when it makes sense. Vulkan makes sense. That's the thing about Vulkan. It makes perfect sense, but it also feels intentionally obtuse like that. So there's a lot of intentionality about it. It feels like it. It's just like, yeah, somebody just like wants to fucking mentally break you. Anyways, so all of that does make perfect sense. So otherwise, like, nobody would really fucking use it. Now, what we have in here? So create compute pipeline. So we need to load the shader, right? So we need to load the shader. So I kind of like this thing that the shader is actually, like, compilation of the shader is put into a separate stage. Well, I really kind of like about it, right? So because it was kind of annoying in OpenGL to just call all of these functions and stuff like that. No, just make it part of the build, right? So I think it's kind of cool. So where is the CPP? Where is the CPP? So we are reading the whole thing. So file length in Nob, it is actually kind of easier, right? So because I can have string builder code. I'm gonna make it like that and read the entire file. And what's gonna be the file? Here's an interesting thing, right? So now I kind of need to know where the file is located. So can I have something like path.h, right? If not defined, path.h, define, and if, right? So we can do nob.c. Just put it in here and include path.h and main.c and include path.h. Path.h. So in here we can actually use the same stuff. So we are sharing the information between the main code and the build system. Main SPV. So this is the path, then I'm taking the code, right? So I'm taking the code, and if it fails for whatever reason, I just return 1. So in here, what I want to do actually, I want to maybe say how much we read. So shader path, const char, shader path. So S contains bytes. S contains bytes, shader path. Code count. All right, so what do we have in here? Didn't compile, but let's actually, oh yeah, I never actually included nob. Look at that, nob.h, define nob implementation. Define nob implementation, there you go, we can even try to run it. There you go, it contains 292 bytes, so we already kind of read it. So after that, shader module create info. We just associate these bytes and file. Ooh, is file length in bytes, or is it like literally we can't know unless we read this function? Oh, it's even by reference. God fucking damn it. Okay, so I swear to God, if it's just divided by size of file size padded. Ooh. Ooh, it is not just so. Why do you do seal, bro? Bro! Fucking, are you serious? The fuck is this shit? Disgusting. So it rounded up, actually. It is rounded up to, you know, to 4 bytes. Graphics programmers don't know. Yeah, that could be the case actually, because they primarily work with floats, don't they? So it is recorded by mathematician hands. Yeah. I have a little bit of experience in competitive programming, and in competitive programming, usually it's done like this, right? So you can do with integers and shit. So, but I mean, it's fine. I guess it is fine. All right, so file size padded. So it is padded specifically. I'm really confused. Right, so the code. Oh my god, can you just go back to where I was? Okay, so, okay, and this is the core. Code size. So the P code is array of U32s. Right, it is array of 32s. But then the code size is in bytes. That is bizarre, to say the least. Right, and it's actually very easy to shoot your leg, I think. Of course. Of course. So it's probably part of kind of like a different extension or something like that, which actually makes me worried. Do I have to query special additional extensions? So what's that? 2.5 hours. Okay, so can I open this thing? This is unopenable. This is not what I'm looking for. So maybe we can take a look at this thing, which is definitely not. Yeah, this is some sort of C++ wrapper or whatever. Let's take a look at Google, right? DuckDuckGo is obviously useless. So create info. All right, so this is unopenable, right? Why does set Vulkan P code? Okay, somebody. Okay, so people talking about it. To type, I find fuck off Google. Hope you go bankrupt. So everything in sperm v is based on the word size 32. If values are less than 32 bits, the value must be in lower bits. If shared code is not superior, then the driver will probably just custom. Okay. Create module. I just want an official description of what it is, and obviously I don't have an access to that because fuck me, I do not deserve that. Obviously I do not deserve that as well. Obviously, fuck me. So none of the usual useful information is available to me. So LWJG blah, blah, whatever the fuck it is. Okay, I guess we'll never know. I guess I will never know. You guys probably know what it is, but I do not deserve to know what the fuck any of that means. So anyways, so CPP. And so the file path, I want to, it's really confusing. Like the fact that it's U32, but then it's in bytes. And on top of that, it's padded in bytes. Why would you freaking define it like that? If it's U32, define it in U32s. And in that case, you don't even have to pad it. So is Vulkan spec blocked too? I guess. Like I don't care anymore, honestly. Like I literally don't give a shit. I just want to, you know, explore some interesting things, right? So learn something new. I don't give a shit. Whatever. Blocked. Next website. Next website. I don't have mental capacity to think about that anymore. So yeah, I just want to double check that. Furthermore, this one is kind of weird. Right, so they are additionally padding it. Right. So they're additionally padding it. And by the way, this is probably something that we can do. And I think I even have that in Nob, don't I? So pad. Holy shit. I have SB pad align. What the fuck? I literally have a function for that case. Holy shit. So I can do code and then I can do size of U32T. The fuck? I forgot that I implemented this function in Noble, right? So you can basically load file into string builder and then you can pad that string builder to a specific, you know, alignment. So it's kind of cool. So that actually solves this entire problem, I suppose. Anyway, let's continue. So I'm creating that, right? So that's the thing. That's the thing we're doing here. So this is a type shared module info. This is the code, but in this case, it's going to be items. I'm going to convert it to voice star, and the file length is actually code count, right? So that's what we're doing here. Right. So this one is not finished. Create compute pipeline. So let's go ahead and just try to run the whole thing. Okay, so it went through everything compiling here. So afterwards, we have to create shader module, right? So we're creating a shader module like so. And okay, assert, maybe put it in here. So res vk success. So afterwards we vk pipeline shader stage create info. Holy fuck, you motherfucker. Holy shit. Alright. vk type pipeline shader stage create info. Okay, so compute shader module. So what is a compute shader module? This is exactly... and we never really... though, how did it fucking work if we... Yeah, so I probably never tried to compile it. So this is a vk shader module. Though, I suppose this is thing... yeah, so it's that stuff. Can I go back? Yeah, so and I have to specify the name of this thing. Create shader stage, pipeline layout create info, pipeline create info, and then you fucking finally create this entire shit. Alright. Holy fuck. So this is main. So then we create pipeline info. So assert. So then we do that. And then we have to do this kind of shit. So to tie all of that stuff together. It's so fucking crazy. It's insane. So res and then 7. Yeah, like that. So this one, yeah, so basically finished this part, hopefully. Okay, so this one pipeline layout is probably a thing that we have to define there as well. And it's going to be sort of like shareable between different stages and everything. So here is the pipeline. Yeah. Okay, that's pretty cool. And so far, at least nothing broke, but it doesn't really mean anything, right? So, doesn't really mean anything. Okay, so can I go back to where I was? Right, so this is a create compute pipeline. So then create command buffer. Right, to create command buffer, we... Oh my god. This is so bad. Holy shit. Okay. So command buffer. So in here we created compute pipeline. Right, so create command buffer. Okay, so I'm literally copy pasting all of these things. So Q family index. And this one is kind of interesting because I think I have deviation in terms of like how I call this specific thing, right? So, but let's just give it a try. So this one has to be res, right? It's going to be assert res equal vk success, equal vk success. And all right, so family index. How did I call that? I think it was index, yeah, compute family index. Q family index, I think that's what it is. But I need to double check that, by the way. I need to double check that. Q family index, how do we... Yeah, so get Q, compute Q family index. Within this thing, we're specifically looking for Q. Like they're doing it literally the same way we do that. And also they checking that Q count is greater than 0, but as far as I know, it's guaranteed that it's greater than 0, I think. So we don't have to really worry about it. So far they're doing it the way we do that, so it should be fine. All right, so yeah. All right, so this is a command pool, and where do we get command pool? Is it defined? I suppose that command pool is one of these methods that kind of get exposed in here. So there we go. So it seems to be compiling, but again, doesn't really mean much. Doesn't, and this one, by the way, has to be something like this. So the next one, allocate buffer. Luckily, all of that stuff is actually pretty copy-pastable, right? Doesn't require like a weird selection strategy, like in case of if you have several queues or several kind of like capabilities, you need to raid them or do something special. So far, it's just like, you know, just a grind work. All right, so it doesn't require anything particularly fancy in here. Just do all of the boilerplate. Just do all of the boilerplate. Okay, so this is the resource. And then the resource, what am I even talking about? Resource equal vk success. All right, and command buffer is something that we need to allocate in here. All right, so this is the command buffer. All right, and okay, so we reached that specific place. Can I go back? Okay, so we're gonna take that. All right, so we're gonna take that. I still don't want to introduce that particular macro because it kind of forces me to still sort of look at the copy-pasted code. All right, so we reached that place. All right, so here we're creating all of the pipelines, and here we don't even check their results. I suppose they don't matter. Is that what the code is trying to tell me? All right, so that's what it's trying to tell me. None of that matters, and all of that. Oh, I need to look through that code because this is weird. What the fuck am I even looking at? What the fuck am I even looking at? So we create a bind a descriptor set. So, all right, so this is the descriptor set. We already allocated it up there. Yeah, we need to look into that. What the fuck is that? And why is it using like ceiling and everything? Work group. Work group size. Is it allocated anywhere? So yeah, we're splitting everything by work groups. I want to take a look at this thing. Core.h group count x, group count y. So you literally splitting all of that stuff by groups. This one is interesting, actually. So you can even sort of customize how parallel all of that is going to be. That is kind of cool. So you can customize the level of parallelization, and even in terms of z, right? So because, yeah, so does it affect like a z buffering and everything? Huh. That's really cool. I kind of like that. Anyways, so but in terms of z, since we are generating like a one-dimensional image, I suppose it's just going to be 1. But to be fair, if your work group is divisible, like if all of that stuff is divisible by work group, does it really matter? Or does it have to be exactly, you know, 32 bytes? It's kind of weird. It's kind of weird. I can do a lot of things. Thank you so much. So what do we want? Maybe yeah. Okay, so this is gonna be something like that. Just want to do that in integers. I just want to do that in integers, and we're gonna divide it like that. Though, just a second, where was it? Or yeah, so this is just a division. Yeah. Yeah, I guess that's fine. So our group size, and it doesn't fail, right? So that's what it's trying to tell me. It returns void. Okay, cool. All right, and there is this thing in here, and VK and command buffer, and recording commands. Recording commands, huh? So we were recording commands this entire time. So there's a VK begin. Yeah. So we start recording commands, we do some commands, and we end recording. So, so command buffer can hold the sequence of replayable commands. That's what it is, right? So you create a command buffer, then you record a bunch of commands, it appends them to that command buffer, you end recording, and you have this sort of like a sequence of commands that you can replay in a loop or something like that. So that's how it works, if I understand correctly, right? And that's what the command buffer is. I think that's what it is. All right, so gets cleared after executing, I think. Oh, you basically populate it on each iteration, right? So if you have some sort of like a loop, right, you start recording commands, you append a bunch of commands, then you schedule them into queue or whatever, probably, I don't really know, and then you clean it up and maybe create another sequence of commands. Okay, so it's sort of like a dynamic array of commands, right? So kind of an interesting way to think about it. Dynamic array of commands. And by the way, this one, right, so this is going to be a result, and we're going to assert that result is equal to VK success. Is equal to VK success. VK success. And so far, so good. Great. Create command buffer. All right, so finally run the recorded command buffer. Ooh, so we're about to run this entire shit. Probably nothing good is going to happen, but we'll see. We'll see. So let's go to here. Okay, run command buffer. So CPP run command buffer like that, and let's just. Seems to be working. Okay, so this is all of the fences and everything, so we have to also check this kind of shit. So it's gonna be assert VK success. Alright. Seems to be fine. So VK Q submit. VK Q submit. Rest like that. Okay, so Q. That means I haven't exposed. Yeah, so it's compute Q. All right. It's just a compute Q in our case. All right, so that's great. Everything seems to be going well so far. So then we wait for the fences. All right, so we're waiting for the fences. Do we have a fence? I think. Yeah, so it creates a separate fence in here. All right. Wait for the fence and then destroy the fence. Huh, interesting. Destroying the fence. Okay, so that's what? Record run command buffer. Okay. So that means it already. Does that mean it already did the thing? It might actually mean that it already run the stuff. Because we reached the point. we reach the point where we already saving the rendered image finally. And this is interesting actually. So we map in the memory and stuff like that. You know what I want to do before we save the image and stuff like that? I want to try to update this stuff. Specifically, let's go to the compute shader. I'm not really sure if we need this kind of stuff. So there's a layout. So here we're just getting the work group size, right? And it's kind of like the same information as we have in the main program, right? So yeah, so I suppose we want to copy paste this information. It's going to be very important for us. So then we create a layout. So we specify this kind of thing, and I do remember this information. Yeah, I guess we have to do that for whatever reason. All right, so the next thing, so we have a structure which is a pixel of a vector 4, but can I just you know, directly, like, do I have to specify it like that? Can't I just have vec4? Like, I don't want to have the structure. It's kind of stupid. So just have this buffer, and that's going to be the output of this buffer. And furthermore, so here's the, here are the like global invocation ID and whatnot. We may want to try to do the following thing. All right. So image ID value, can I assign directly some sort of a red color in here? Vector 4, 1, 0, 0, 1. So just fill everything with red. So is that something that is going to work? Let's see. It didn't compile properly because I did a syntactical error of some sort. Did I forget? What did I forget? I don't get it. So what does it even say? Syntax error, unexpected identifier, expected left break. Okay, so it's probably wrong version of the shader or whatever. So because here we use 450, and maybe this is exactly what we have to do in here. Or maybe, yeah, that was the problem apparently. That's just a wrong version of this thing. Yeah, so that compiled successfully, more or less. Hopefully, we'll be able to run it. So if I do run it, nothing really broke, but again, in case of Vulkan, you never really know anyway, right? You never really know. So yeah, let's try to save this entire thing. Let's do memory map. Okay, so I'm gonna go to main.c. This is not main.c. Here it is. So it's gonna be save image. All right, so we're saving the image. So we need to memory map some of that. All right, so here is the memory mapping. Then, yeah, it's doing kind of a weird thing. So PM mapped memory. I see what's going on here. I see. So we don't really have a pixel. So in this case, it has to be V4F. Right. So that's what it is. So this is a mapped memory. And we can have this kind of stuff. I think I need to bring STB image. Let's go ahead and bring STB image. Nothing's STB as a third-party dependency. So STB imagi. So it's going to be row, right? So I'm going to put that stuff in here. Let's just put that stuff like that. Include define STB image implementation. STB image implementation. So yeah, buffer memory undeclared. So what that means is that it has to be taken from somewhere. That is bizarre. Yeah, because buffer memory, it's a VK device memory that I actually called differently in my code, and it has to be exposed, I feel like. Yeah, it has to be exposed. Device memory, I think, yeah, that's the only place where we have that. So, and that is basically that. Buffer memory is just a memory. What else we have? What you don't like? Expected extension, expression. Okay, so yeah, everything's fine. So okay, so we're starting to use math in here, and we never linked with math. So let me go to node.c. So we're getting somewhere, chat, by the way, we're getting somewhere. So this is math. This is math, and yeah. Holy fuck. All right, so we map the memory. So where is this save rendered image? Here it is. So we need some sort of a array into which we're going to be saving all of that stuff. And what I'm thinking is maybe I'm going to have something like struct pixels, and it is going to be uint32. Doesn't really matter. So I might have as well actually just do something like that. Pixels is going to be string buffer. So in here, I can just iterate. So int 0 width multiplied by height plus I. Right, and in here what they do, they're actually, oh yeah, it's a pretty fairly standard thing to do. Right. I can even call it image, right? So I can literally use the same trick in here where I do di append, and I'm appending into the image all of that stuff. So does it? Yeah, we do need that stuff in here. So we literally use di append, and then we should not forget to unmap the memory, right? Unmapping the memory, so it doesn't compile because. Yeah, so in all of these cases, it's actually X, Y, Z, W, in our case specifically. This is just a memory, in our case. Ooh! Did you notice that? Do you see that? There is a visible delay between this line and this line if you enable this shit. There's like a visible delay. I think you can even feel that. We are not saving anything, but there was already like delay. It's doing something. It is doing something. Holy fuck. All right. So, and then we just have to save this and that. So I suppose maybe it takes time to transfer that image from GPU to CPU. Maybe that's what's going on. I don't fucking know. We'll see actually. So STB image. Oh fuck, I need STB image right. This is a wrong one. So maybe I need to download. So it has to be right. GPU magic, yeah. wget and let's go to main.c. STB image right, and then right, and fuck. I didn't mean to do that actually. But I meant to do something like that. Okay, so now in STB image right, STBI write PNG. Let's just write PNG like that. Okay, so the file name is going to be output PNG. So width, height, amount of components is going to be 4. The data itself is an image items, and a stride in bytes is width multiplied by 4, I suppose. Obviously, this entire thing may fail. Right. So let's do something like this. Output path. Output path, and okay. So maybe not log error. could not save file as so the output path return 1. Fuck you, motherfucker! Fuck yeah! That's what the victory tastes like. Holy shit. Chat, we did it. Chat, we did it. First try, without validation layers, motherfucker. Without validation layer. We actually copy-pasted third of the code, right? So, but 2/3 of the code, I think we were trying to genuinely understand what the fuck is going on. Oh my god. How did it work just first try? What the fuck? The delay is probably the PNG encode. I disagree. Because delay was before we did PNG encode. I'm gonna disable PNG. So no PNG. Look at that. There's still delay. That's the thing. There's still delay. I think it is literally like mapping. Okay, we can try the following thing. So what if I just do only mapping? Right, so just map and unmap. No. Huh. Nope. No fucking way. I feel like it's iterating this stuff. Holy shit. It's the loop. Because we mapped the memory, so every time we read from that memory, the CPU probably does a round trip to GPU for each individual byte. It might be actually it. This is hypothesis. Maybe some sort of page fault or whatever, yeah. It's kind of interesting, actually. The memory is already in host. No, I have no idea, but for some reason, this is a slow operation. And it's not just like we measured it slow, it's perceivably slow. That's how fucking slow it is. So it must be somewhere far, far away, or just doing some additional shit. What's the end goal with Vulkan? Do something with compute shaders, right? So just create a compute shader, some sort of a computational payload, and execute it on GPU. And I suppose it was achieved, right? It was kind of achieved. So one thing we can do in here, by the way, we can do the classical thing, where I just, you know, I'm gonna find the column, right? So let's do something like, I fucking know, 32 or work group size, right? So I take that, and this is, I suppose, is going to be X, and I kind of want it to be maybe floor. Can I do shit like that? Yeah, okay, I probably can do it like that. So it has to be X, by the way. This is gonna be Y, and this is gonna be Y, and then back for caller X plus Y. X plus Y divided by 2 equal to 0. In that case, it's going to be that, otherwise it's going to be black, right, and then here it's going to be color, something like that. So, which also raises an interesting question. Can I merge together these two things? Not quite sure, but anyway, so equals global float to temporary high precision int. But what if I explicitly cast it? Is that something I can do? Syntax error. Maybe I have to call it like a function. Yes, I can do that. It didn't work. Fascinating. All right, that's getting interesting. Oh wait, I forgot. All right, let's get rid of all of that. Let's get rid of all of that. And boom, there we go. It's pretty cool. Execute it on GPU. On GPU. It's interesting. Interesting. You know what would be cool to explore next? Again, programming directly in SpermV. Right now I have a setup where I can directly program in SpermV, which is really interesting. Would be also interesting to somehow decompile this entire stuff and whatnot. That's a good idea. Yeah, sounds like fun. Actually sounds like fun. Yeah, so HDR, write HDR to write floats directly. We can take a look at that. STB image, write HDR. I never heard of it. So what HDR stands for? High definition, or what is that? I don't really know what HDR stands for, but I suppose it just accepts floats. B to SpermV compiler. Yeah, we can try high dynamic range. Okay, so it's high dynamic range basically means that the components are floats, normalized floats, right? So that's what it means. I see. I find this session extremely dissatisfying. I find today's session, not even today's session, but the Vulkan session extremely dissatisfying, because I got so demoralized that I started to just copy paste these chunks of code without trying to understand them. And I'm not happy with how it went. I'm really fucking not happy. I achieved, again, yet another case of I hit the target but missed the point. Right. And I hate when that happens. I really hate when it happened when I hit some sort of a target, but I kind of missed the point. So, and the point is to understand this so I can rearrange this code in a new way that is not really present in the examples. It's really hard to explain that, but I hope some of you understand what I'm talking about, right? Because here's the thing. So there is a very copy-pasty APIs like OpenGL and whatnot. And there is a kind of like a finite amount of examples, and everybody is copy-pasting from those examples. And if you look around at the code that is in the wild and in production, you can clearly see that everyone is just copy-pasting from the same place. Everyone is literally just copy-pasting the same code from the same place over and over again, but nobody is synthesizing this code in a new novel ways that utilizes actual understanding of what this API is doing. One of the things that I did some time ago, which I didn't really see in the wild, but maybe there is something like that in the wild, but one thing that I never seen in the wild is how I generate a quad for OpenGL. Right, so I have an OpenGL template, right, and it actually generates a bunch of quads, right, and it generates a quad on a vertex shader, and I think we managed to come up with that ourselves, so maybe somebody helped me to do that, but essentially what we utilized in here, we generate vertices of the quad based on the vertex index without ever creating vertex buffer. So the cool thing about this specific example is that it never creates VBO or anything like that. It's just like it only creates a vertex shader and a fragment shader, and that automatically generates all of the necessary vertices and just slaps the texture onto it without forcing you to create all of the buffers and stuff like that. And it utilizes a slightly deeper understanding of OpenGL than just copy pasting the examples. You see? The reason why I'm trying to understand APIs is that then later I can synthesize a simpler examples that are usually not present in the copy pastable code. It's really difficult to explain what I mean, but if you programmed long enough, you probably understand what I'm trying to say. You can always hit the target. It is easy to copy-paste code. What's difficult is to produce new copy-pastable code. Because this thing, already copy-pastable, right? I don't need to synthesize this code ever again. It's already kind of neat copy-pastable trick, right? It is easy to hit the targets. It is difficult to get the points and produce something new and novel. And that's why I find this Vulkan session extremely dissatisfying, because the API gatekeeps itself from understanding it deeper, at least for me right now, maybe later I will understand it deeper, to produce and synthesize code that is probably much simpler, right? It's kind of cool that I literally achieved what I wanted, but I'm still extremely dissatisfied. And that's why I got angry, by the way, because I knew that this goal of trying to understand it a little bit deeper is kind of getting away from me. So I think whenever someone breaks through the Vulkan ass filter, no one wants to go back and provide people's better tutorials example. Yeah, I suppose. So what you want to understand is surrounded by stuff you don't care about or understand. Yeah, that's the thing. And ironically, don't be angry because of this. Being annoyed by bullshit is a superpower. After 10 years in web dev, I got such a high tolerance to this bullshit that sometimes I'm actually not aware that I'm dealing with nonsense and need to cut it. Yeah. So, what was the goal? Use or learn? Why does it have to be two separate goals? So why there's like this false dichotomy that, you know, you can only use or learn? Why it's not both? Why it's another third thing? So like I don't understand this kind of mentality of the industry that understanding has no utility. Right, obviously understanding has utility because it produces new copy-pastable things. But everyone is so wind up in this weird rat race that they refuse to fucking see that, including myself sometimes. So I'm not immune to that as well. It's just like we're in this hamster wheel and we're not allowed to just like stop for a second and think. So yeah. But anyways, I guess that's it for today. Thanks everyone who's watching me right now. I really appreciate it. Have a good one, and I see you all in the next recreation programming session with Mr. Azuzin. So yeah, love you. Mwah.